We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Okay, friends, welcome back. Let us start learning of chapter number 8, potpourri of multiple reactions. So, potpourri means a mixture of people or things. So, now we are going to learn the multiple reactions, which can be a mixture of parallel reactions or series reactions. Means parallel and series reactions as a multiple reactions. In chapter number 7, we have seen specifically parallel reactions, and we have find the maximum possible product formation and how maximum concentration of the desired component we have tried to find out in the rate expression for the desired product. So now in these reactions we are going to see the further series parallel combination multiple reactions and how we can find out the best possible solution. Fine. So now we can see here that it can be a so as shown over here, so it can be a series reaction, or like here it shows series reaction for A gives R gives S, and S gives T, but it is parallel reaction simultaneously for component B. So it is a combination of series parallel reactions. Fine. This is again Denbig's special consideration, which we are going to discuss in the end of the chapter. So series reaction, either the irreversible or reversible, this becomes reversible reactions. Fine. Both reactions are going to be reversible, or it may be a cyclic. Fine. Can be represented like this. Fine. So from like in this series reactions, your S can give only R and R only gives A, but here in this case both R and S may be converted back into the A directly. So it is a cyclic reaction network can be there. So like any combinations of series parallel reactions it can be, and now we have to analyze it. So now let us analyze this first reaction where A gives R gives S, where rate constants are K1 and K2. Fine. So now depends on the definite value of K1 and K2, but here depends on the concentration how the product distribution can be achieved, that can be analyzed. So we can give that what is the rate of consumption of A, that is minus K into C raised to, and definitely we are considering is a first order C raised to 1. So rate of formation or rate of change in concentration of R can be given the rate of formation of R, that is K1 into Ca by the first reaction, whereas being consumed minus coming here picture K2 into Cr, and rate of formation of S, that is K2 into Cr. So this all we have not mentioned any minus sign over here, just its corresponding consumption or formation is shown by change in the sign. Minus shows as a consumption, plus shows as a formation. So now what you can see here, so when you carry out a reaction in this particular reactor, fine, so what you can see here, so it's a simple batch reactions with some stirring, there is no inlet outlet, but what is the matter is that you provide all energy to the whole reactor. Fine. So energy given to the whole reactor, which is in large quantity definitely. So in this case what you can see, the concentration of A is being always means continuously decreases, that is expected because no formation of A, only consumption. So A is changing like this. So but and S is always increasing, means it is always forming, no consumption of S, it is always forming. So A is being consumed continuously, A is forming continuously. Only R which is forming initially, so concentration of R increases it reaches to the maximum and then it decreases over the period of time after a certain point of time. So that's what we are interested to. Most of our objective is to find, because if R is intermediate product, if R is intermediate product is a desired product, fine, our desired product formation is R, we are interested in R, not in S, then our intention is to find out at which condition maximum R is formed, what is the maximum concentration of R we can achieve, and what time we can get it, fine. If it is a batch reactor, after which time we are getting the maximum concentration of R, fine. So this is what is going to be an objective. So now just check how the contacting pattern is going to affect the concentration. So now if you change the small point, now instead of just, we are still using a batch reactor, but instead of providing all energy at a to total reactor, if you provide energy only to a small segment of the reactor content, fine. So we are taking out small portion of reactor content, it passes through one small such portion of reactor or some other vessel, and when it comes out it is recycled back, fine. So it's essentially infinite recycle, fine, complete recycle, where we are providing the energy only to small fraction on this reactant content. So now what you are expecting, fine. Now what you can see that there is A and S, like definitely A is always decreasing as usual, fine. S is always increasing, but only the thing concentration changes. Now what you can see, there is no formation of R as such, means whatever R is formed, it has been converted to the S immediately. This means that we are not getting a significant amount of R. We cannot see substantial formation of R inside the reactor, fine. So what happens here, the energy provided over here, it just converts all R into S, because again depends on the K1 and K2 value, again I repeat, fine, but still it says shows that when you provide energy to only small portion, fine. So what is happening, as early as A is converted into R, so it shows that sufficient temperature is available. So as early as A is converted into R, R is simultaneously converting into the S, fine, because no other A is available to consume this energy. Energy content is very large, and that's why it easily convert or produces the S. So which is probably, if our interest is in R, desired product is R, then definitely this contacting pattern is not going to be good one. Yes, definitely if you are interested in S, then it's fine, but otherwise if you are interested in R, this is not going to be a good contacting pattern, fine. So for the irreversible reactions in series, fine, so it's very clear. So all the reversible reactions in a series, the mixing of fluid of the different composition is the key to the formation of intermediate. So what extent of mixing we are getting it, the maximum possible amount of any and all the intermediate is obtained if fluids of different compositions and at the different stages of conversions are not allowed to mix. Definitely in coming few slides we are going to see this sentence in more details, you can come to know, fine. So now if you see that how the contacting pattern, we have already seen this in the previous chapters, like definitely plug flow, there is no mixing is taking place, fine. So within a plug flow, as per the characteristics of the fluid, there is no mixing, fine, and velocity profile is flat, whereas this is what is 100% mixing is taking place, fine. So left scheme is better, in fact the best possible flow scheme for all the kinetics favorable reactions where order of reaction is greater than 0, fine. Definitely means more accurately it's a 1 we are saying it. Plug flow pattern with some recycle, definitely as the recycle ratio increases, we learn that it is converted into the MFR mixed flow reactor. So in this case, as R increases, as the recycle ratio increases, fine, it becomes mixed flow reactor. So and you know that if is a single C, instead of single CSTF we have multiple CSTRs, and CSTR in series gives equivalent to the 1 PFR. So now looking to the 6.5 and 6.6 and 6.16 and 6.7, and if you remember, then like this both shows that how the PFR and MFR performance, this two graph are the performance comparison. In chapter 6 we have learned that how the PFR and CSTR performance with reference to first and second order reactions only, whereas this is for the recycle condition 16 and 17 for the recycle ratio. So as the recycle ratio increases, fine, so it becomes PFR. So chapter 6 we see that left is closer, so it shows the left is closer to the left for both the first and second order reactions. So we generalize it to any positive order reactions, and left reactions, left flow reactor with a small reaction recycle is better option definitely compared to the two reactors in CSTR in a series, definitely. So this is better option definitely compared to the two CSTR in a series. Now two CSTR in series, but what is the difference you can see here? You can check it out, the feeding pattern, fine, which is better. So now in this case what happens, second reactor, this you are feeding to the only first CSTR and exit outlet of the first CSTR enters in the second CSTR, whereas in this case what you are doing, you are feeding to the first as well as second CSTR, and out of first is going into the second, like that. So definitely which one is better? This is because this is perfect example of CSTR in series. Whatever conversion takes place, then only it enters in the second reactor, then it goes to the third reactor, like that. So right pattern in this case, definitely this is going to be a better choice. And definitely laminar and plug flow reactor, and little bit different view in this case. Here it is mentioned that turbulent flow has less intermixing of fluid of different ages by bypassing. I am little bit different here. We have learned that turbulent flow has more iris formation, and that's why mixing is more, but more better velocity profile. Fine, all of you have learned that velocity profile of turbulent flow is much more flat compared to the laminar. Laminar has a parabolic flow pattern. So in this case also, like residence time of all the fluid, what we are saying, residence time of all the components of the fluid is going to be same in case of turbulent flow rather than laminar flow. While laminar flow has a different velocity profile for each layer, and that's why that resonance time is going to be different. In theory 2 we are going to learn more in this regards in a non-ideal flow pattern, but for just your information, so I am considering turbulent flow here better because of much better velocity profile, means velocity of each layer is going to be constant, right? So this velocity profile, it's going to be flat like this, fine. So we are considering turbulent flow is better, and anyhow we are considering all the pipe flow as a plug flow reactors. Fine. So now quantitative treatment of the plug flow batch reactors, we have analyzed the situation basis. Now we are going to have some specific with reference to material balance and then correlations. So now as it is, we are considering this, A gives R and R gives S with the constant K1 and K2. Fine. So if we put it again in terms of if it is a batch reactor, then CA by C is 0 into e raised to minus K into T, or if it's PF, it becomes e raised to K1 into tau. And concentration of R with reference to C0 can be given by this correlation. To some extent we have seen in chapter number 6. Chapter number 7 definitely we have come across this correlation, concentration of CS. So if I carry out a reaction from a particular reactors, and what is outlet concentration can be there in a outlet stream, that can be defined based on this three correlation. What is the concentration of A, R and S? Fine. So this is simply balance at any point of time, because 1 mole of A gives me 1 mole of R, and 1 mole of R gives me 1 mole of S. So if you started with Ca0 equal to some numbers, and Cr0 and Ca0 is 0, then definitely at any point of time your total number of moles is going to be equal. So you can say that any point of time Ca plus Cr plus Cs is equal to Ca0, provided initial concentration of Cs and Cr is equal to 0. Fine. So that is what is our material balance. So if I know A and R, we can if you know the concentration of A and R, we can find the from calculation concentration of S. So we can give this correlation. Derivation is not that definitely, just we are accepting it. CR maximum concentration of R can be, it is, now if you note that this purely depends only on the rate constant, fine, K1 K2 divided by K1 by K2 ratio whole raised to power of K2 upon K2 minus K1. There is no dependency on concentration, so please check that it is not going to depend on the concentration of A or R or S. It's completely based on only rate constant, fine. So just rate constant value will decide, fine, how this concentration profile is going to change, and optimum time at which we are going to get the maximum CR, that can be given by 1 upon K log mean ln of K2 multiplied by K1 K2 minus K1. Again, this is interesting, you just try to derive it and try to learn it, how we can get it. So this is also the point at which the rate of formation of S is most rapid. How to analyze this? So where the CR max, fine, CR max, now S formation is, how the rate of formation of S is given by CS, RS is nothing but K2 into concentration of R. So when the CR max, it is going to be the maximum rate of formation of S, and that's why I mean CR concentration max, but it is the rate of formation of RS that is going to be maximum, fine. When this graph, individual graphs, you can see this to some extent now. So when this becomes maximum, the rate of formation, the slope of this line is going to be maximum. It is, slope is increasing, this is going to be highest slope, and then after it is again decreasing. So rate is nothing but the dCs by dt, or what I think dc by dt. So that is going to be tangent at this point. It gives me the maximum value of RCR max, but rate of change in concentration of S is going to be highest, dCs by dt. Fine. So these are the correlations, we can use it. This is again interesting graphical representation of this three correlation, fine, A, R and S concentrations. So this shows me what is concentration of, definitely means CA by CA0, that is with reference to the initial concentration of A, that is why maximum value is 1. So fine, when your concentration is 1, that is 0 conversion, and as the concentration increases, fine, when it becomes, when 0 concentration conversion is 0, and when it becomes 1, when outlet concentration becomes 0, fine, when the CA becomes 0, this is, and this is initial concentration when CA is equal to CA0. So 0 conversion, and as the time proceeds, K1 into tau, K1 is the constant, tau is the time, resonance time. So as the time proceeds, your conversion increases. Now it is interesting, fine, you can see this, definitely your concentration of A decreases with time as usual, you have seen in a previous case. Just a minute. Document is being saved. Yeah, it's everybody's really right. sorry, it is I was saving the document, so it was interruption. So now it shows that definitely CA by CA 0, that is, so starting from CA is equal to CA 0 with reference to time, concentration of A decreases definitely, as we have seen earlier. So now what is about R? So we have learned that R is should increases to some extent and then it decreases after a certain point of time. So these are the graph of CR by CA0. Fine. So this is what is the CR by CA0. Fine. But so what you can see here, CR by CA0, only particular this graph, what you can see here, this is only for K2 by K1 is equal to 0. What it mean by? So where the K2 is equal to 0, K will be any number. So what do you mean by K2 is equal to 0 means second reaction is not taking place at all. Fine. Second reaction is 0. And that's why what it means, only a single reaction A gives R, and that is only formation of R, and that's why you can see that concentration of R is not decreasing after some time. For all other values of K2 by K1, whatever may be the small K2, fine. So now here if K2 by K1 is 0.1, what you can see that the value of R decreases after some time. So this is what is your maximum concentration it reaches, and this is what is the dash line is the maximum CR value, and then after it decreases. Fine. So now similarly, as what you can observe now, next is as the K2 by K1 value increases 0.1 and it becomes 1, even K2 by K1, both the reactions are moving with the same speed, like for K1 is equal to K2, then again this CR max is reduced substantially. This was much higher, almost in the range of 0.7, now it reduces almost half of, that is around 0.4 something. Fine. And if it increases to 10, so when K2 is 10 times more K1, then definitely your maximum R is going to be hardly 0.1, 0.05 something. And so that is what is the interesting aspect. As the second reaction becomes more and more faster, maximum possible concentration of R decreases substantially. Fine. So that is what it indicates. Now if from where you have to so this is what is your CA curve, this is what is your CR curve. Fine. This dotted line is nothing but the locus of the maximum CR max value at which R is going to be maximum, passing through the maximum points of the particular CR value. So now I can calculate the CS amount of the constant amount of the S product. So again this graph is given in the form of conversion. Fine. This is again the ratio of concentrations. So now maximum definitely with reference to CA0. So and we have learned that total at any point of time summation of CR plus CS plus CA gives me the ultimately CA0. Fine. So now we know that so this is your linear line, what you can see. Fine. That is going to be your ultimately amount of CA.